Speed plays a major role in aviation because it is directly related to the performance of the aircraft. But there is not just one speed. Why don't we get a deeper insight into the different speeds and their definitions?
Okay, for an after crossing, turn right.
Foxtrot Delta Delta 0, wind 270 degrees, 16 knots, runway 02, cleared for takeoff.
Welcome back. My name is Frank Dreyer and I'm pleased that I could arouse your interest with today's topic. Let's get right to it and start with a speed that is actually quite familiar to us from our daily non-flying lives. And by that I mean the ground speed. It is a speed at which the aircraft travels a measured distance above the ground per unit of time. We can actually compare this with the speed of a vehicle on the road. The ground speed can therefore be directly related to the true airspeed, namely ground speed is equal to true airspeed corrected by the wind component. I will come to a detailed definition of true airspeed in a few minutes. In aviation, with the exception of gliders and microlights, speeds are expressed in knots rather than kilometers per hour, and distances are given in nautical miles instead of kilometers. Here, 1 kilometer per hour equals 0.54 knots, i.e. 100 kilometers per hour corresponds to 54 knots. 100 kilometer distance corresponds to a covered distance of 54 nautical miles. So if we had covered a distance of 100 kilometers or 54 nautical miles measured over the ground in 1 hour, we would have flown at a speed of 100 kilometers per hour or 54 knots ground speed. With a car, the speed is easy to calculate because the turning of the wheels connected to an associated gearbox can easily measure a distance traveled, then you bring it in a relation to the time you needed for it. Long before gyro platforms and GPSs were invented, the only way to calculate aircraft speed was by pressure differences. When the aircraft is on the ground, there is only one pressure, namely static pressure, abbreviated PAT. For this purpose, there are static pressure transducers on the aircraft, so-called static ports, which transmit this pressure to the speed instrument. In addition to the static ports, there are also pitted tubes which measure the total pressure, abbreviated PT, via a tube aligned in the direction of flight. In my presentation, you read the term multifunction probe. In the case of the Airbus 380, this assembly includes not only the pitted tube, but also an angle of attack measuring device and an outside total temperature sensor. The total pressure is the sum of the atmospheric or static pressure and the dynamic pressure, abbreviated PD. As soon as the aircraft moves, the dynamic pressure is added to the static pressure. The pitted tube measures the total pressure. Depending on the design, there is also an additional pickup for a static pressure on the side of the pitted tube, like here in my example. Now, by subtracting the static pressure from the total pressure, the dynamic pressure can be calculated. And with that, we have our next speed, the indicated airspeed, IAS. Today we find the speed primarily in single-engine piston aircraft. It is the airspeed relative to the surrounding air mass calculated directly from the pressure difference between the total pressure and the atmospheric or static pressure. However, it has certain inaccuracies. Because the static ports do not always measure the correct pressure, as the air mass also flows around the aircraft, and these variable airflows falsify the measurement results. Likewise, the static air pressure decreases with increasing altitude because the air density decreases. At higher altitudes, the indicated airspeed is therefore lower, while the speed is actually the same relative to the surrounding air mass. Our next speed is the calibrated airspeed, abbreviated CAS. The calibrated airspeed is based on the indicated airspeed and with the value key I, inaccuracies in the measurement procedure of the static pressure are corrected. In light aircraft, there is no display for the calibrated airspeed, i.e. a formula is available or tables with correction values are printed in the flight operations manual. In modern commercial aircraft, instead of the indicated airspeed, the calibrated airspeed is continuously calculated in the background and displayed in the cockpit. The equivalent airspeed, EAS, is based on the calibrated airspeed, but it is adjusted for the compression error. The air is disproportionately compressed in front of the pitted tube with increasing airspeed. This leads to a higher air density and consequently a higher total pressure being measured than is actually present. The error is rather small at lower speeds, i.e. below 100 knots, and can be neglected, but then it has a parabolic increase as soon as the airspeed rises above 200 knots. The EAS is not displayed in the aircraft. In commercial aircraft, it is calculated and processed internally for the control systems, among other things, since it is directly related to the aerodynamic conditions. Let's move on to the so-called true airspeed, abbreviated as TAS. The density of air decreases with increasing altitude, and with it the static pressure. This means that with the increasing altitude, the aircraft must move faster forward in the surrounding air mass in order to build up the same total pressure to generate the required lift, since the static pressure has decreased. That is, with the same calibrated airspeed but increasing altitude, the true airspeed increases. So the true airspeed can be calculated from the equivalent airspeed by just considering the air density, or from the calibrated airspeed considering air density plus the compression correction. Let's look at a formula for this. Phi0 is the air density at sea level. Phi is the current air density around the aircraft. K is a correction factor for the compression error. The factor K is not the same at every speed, so it must be obtained aircraft specifically for each speed from a table in the flight manual. In case a true airspeed is displayed in the aircraft, it's calculated internally. True airspeed equals calibrated airspeed times the square root of Phi0 divided by Phi and multiplied by K. This looks more confusing than it is. Let's take a look at an example. As initial values, we take a flight altitude of 4,000 meters, which corresponds to just about 13,000 feet, speed 250 knots, calibrated airspeed. Phi0 is the air density at sea level. For simplicity, I take the standard value of 15 degrees temperature and an air pressure of 1013.2 hectopascals, hence 1.225 kilograms per cubic meter. Now we put the values into the formula. Next, we can truncate the units in the fraction under the root. Finally, the following calculation, as units only knots remain, and the result is then a true airspeed of 302.35 knots. So far, we have refreshed the basis of speed definitions. All further speeds, which we will discuss now, use one or more of the mentioned speeds as basis. They always start with a V, and V is derived from the English word velocity, more precisely velocity vector. These V speeds are limiting speeds and find reference to aircraft certification and legal requirements. Before I begin, another definition first, because we come across the expression again and again. What does the critical engine mean? In multi-engine aircraft, symmetrical propulsion is achieved by all engines producing almost the same thrust. The critical engine refers to the engine that, in the event of a failure, would most adversely affect the performance or handling capabilities of an aircraft. In the case of a four-engine aircraft, this would be one of the outer engines. In case of a twin-engine aircraft, it doesn't really matter whether it's the left or the right engine which fails. Let's start with the minimum control speed ground, VMCG. VMCG refers to the controllability of the aircraft on the ground and is only used for multi-engine aircraft because it concerns the aerodynamic behavior in case that the so-called critical engine fails and consequently the remaining thrust is not longer symmetrically available, i.e. a corrective control input on the control surface is necessary to keep the aircraft controllable on the runway. VMCG is specified in calibrated airspeed, and it is that speed at which, in case of a critical engine failure, a pilot with normal pilot skills, so I'm not talking about a test pilot, is able to keep the aircraft under control without the nose wheel steering, but only with the aerodynamical controls. The legislator has still attached some conditions to the definition. The aircraft is in one of the approved takeoff configurations. The remaining engines are set to full thrust. The most unfavorable approved center of gravity position. The trim is set for takeoff. And the most unfavorable but permitted takeoff weight. Under these conditions, the maximum deviation from the runway center line must not exceed 30 feet. We now come to the operational speed definition for takeoff, starting with the engine failure speed. The engine failure speed is a theoretical speed set by the pilot assuming that the critical engine fails. There are narrow limits here because this assumed speed lies between the VMCG and the decision speed V1. The VEF is ahead of V1, which means the aircraft is aerodynamically controllable, but the takeoff must be aborted. Why? Here's the answer: the decision speed V1. V1 is based on calibrated airspeed and is called decision speed for a reason. Would the critical engine fail before V1 it is reached, the takeoff must be aborted and the remaining runway is sufficient to bring the aircraft to a stop. After reaching V1, takeoff should be continued even in case of a critical engine fails or another problem has occurred like a tire blow. V1 varies between aircraft types and dependent on factors such as takeoff weight, runway length, outside temperature, elevation of the airport, choice of flap setting for takeoff, engine thrust used, and contamination of the runway. Therefore, it must always be calculated by the pilots before takeoff. Aborting a takeoff after V1 is not recommended, as per definition the aircraft cannot stop before the end of the runway and therefore a runway overrun must be expected. After reaching V1, it is guaranteed that the remaining runway length is sufficient to perform the takeoff despite the thrust loss of the critical engine. Let's take a quick look at a video. An Airbus 380 in Zurich planned takeoff on runway 34. The runway is 3,700 meters long and 60 meters wide. The Airbus is not fully loaded, so a takeoff with reduced thrust is planned. The V1 is calculated at 126 knots, so rotation speed will be already at 136 knots, which means that the constellation here is such that the long runway and the thrust weight ratio would even allow an aborted takeoff just before rotation speed. That's the advantage of commercial aircraft with a lot of power. In my takeoff, we will suddenly get engine fire on engine 3 and 4 at a speed of 120 knots. We are ahead of V1. Consequently, I decide to abort the takeoff. Then a reaction time of 1 second is considered, so I reject the takeoff in 125 knots. Let's see what happens. AV1 does not exist for single-engine aircraft. Why, you may ask? There's also a critical engine. And that's exactly where we find the answer. If the one engine fails, there's no uncritical second engine left, and hence there's only one way to go, whether still on the runway or already in the air, namely the decision, stay on the ground or return safely to the ground. A pilot has to think proactively. Flying is not like driving a car. There are situations that are very dynamic and things happen very quickly, like the takeoff process, among others. Before I release the brakes, I mentally run the takeoff in front of me and think about actions. What do I expect to happen if a tire blows out before I'm airborne? What will I do if my engines fail shortly after takeoff? How will the airplane react? How do I have to react to keep it under control? So always give myself a briefing adapted to the upcoming takeoff and flight phase. The same applies to an upcoming landing, by the way. That's my approach, and it's gotten me safely through 40 years of flying. Let's take a look at it in practice. I'll take you to Linz in Upper Austria. There's the ideal flying weather today, 20 degrees, no wind and a little cirrus cloud cover. We take an Aquila, a nice two-seater single-engine piston plane. It flies easily and is ideal for a day trip. In Linz we take off from a 60-meter wide concrete runway. Sports plane is significantly smaller than a commercial aircraft, so of course you sit lower. With a 60-meter wide runway, we can expect to feel like we are sitting on the ground. Come on, let's go. We are holding on runway 08 in Linz. The runway is 2,838 meters long and 60 meters wide. The weather is excellent, 20 degrees, no wind. The checks are all done, flaps on half, fuel pump on. Now comes my emergency briefing. In case of engine failure, before rotation, decelerate, fuel pump off, next exit, inform ATC. Airborne up to 500 feet, nose down, and land again directly on runway 08. 500 to 1000 feet, land straight at behind the runway, there are no obstacles and it's a flat meadow. Above 1000 feet, 180 degree turn to the left, mayday, inform tower, and land opposite on the runway. Now I'm ready for takeoff. I release the brakes and slowly push the thrust lever forward. It makes no sense to aggressively give full throttle here. It puts unnecessary strain on the engine, and the yaw moment caused by the torque generated can definitely create lateral oscillations which easily could get out of control, especially on a concrete runway. 60 knots accelerating, I initiate the rotation and plan for a climb speed of 65 to 70 knots. Today we have no crosswind. During the climb, a look at the compass, 080 degrees checked and correct to keep the direction. Engine failure. I push the stick fully forward and the nose must come down, and I unload the aircraft by 0G to take away drag. I reduce the descent rate, stabilize final and set the flaps to full. The prop is turned across due to the airstream. From now on, it's like a normal landing. We see that such a maneuver is not really a problem, but if we hadn't thought about it beforehand, it can quickly end in a disaster. As I learned at the beginning of my aviation career, aviate, navigate, communicate, always in this order. Well, steps 1 and 2 are done. Time to inform the tower. Think ahead. We don't want to block the runway, so no emergency braking here. Let the aircraft coast to a stop by entering the next taxiway if possible. We are back. I guess there was nothing with the trip today. Then we will just continue here. A few minutes ago, we have seen a takeoff reject from the Airbus 380. Such a high-speed takeoff aboard creates a lot of stress on the brakes. And that brings me to another design-related limiting speed. It refers to the braking system of the aircraft. If the takeoff has to be aborted, the brakes must also be able to bring the aircraft, which at this point is still heavier due to the full fuel tanks, to a safe stop. The regulation require that in the event of aborted takeoff, at least on a dry runway, the thrust reverser still available on the engines that are full functional must not be taken into account, i.e. the brakes alone must be capable to bring the aircraft to a standstill. When braking, the resulting friction between the brake pads and the brake discs generates a not inconsiderable amount of heat, and this must be dissipated, heating up not only the brake system and the rims, but also the tires. Both the braking system and the tires must be capable of delivering this power, i.e. energy absorption, in excess of V1. Therefore, if the start data calculation results in a V1 which is higher than the calculated VMBE, the start cannot be carried out in this way. We pilots have graphs available for this purpose. If the brakes are still too warm from the previous flight, for example, and could therefore not absorb enough additional energy, then the brakes must be either cooled down beforehand with special fans, or the takeoff must be postponed. In commercial aircraft, there are corresponding temperature displays in the cockpit for individual wheels. The VMU is the so-called minimum unstick speed. This speed is a design or construction specification for the aircraft manufacturer. It refers to the size and shape of the wing surfaces and control surfaces. VMU guarantees that once it's achieved, the aircraft can safely fly aerodynamically. The default is that the VMU is always less than the takeoff speed VLOF, and I'll get to that in a moment. There are two different types of aircraft depending on their design. The geometrically constrained dependency or constraint that leads to a VMU, which applies to the most commercial aircraft, and the aerodynamic dependency, which applies to high-performance aircraft such as military jets. For geometrically constrained aircraft, the VMU must be at least 1.08 times the VLOF, and in case the critical engine fails, still 1.05 times the VLOF. But enough about that, we don't want to design an aircraft here today. Another design and certification related airspeed is the minimum controlled speed air, VMCA. The VMCA is the minimum speed as calibrated airspeed at which the aircraft is aerodynamically controllable to maintain heading with a maximum of 5 degrees off bank, even though the critical engine has failed and the remaining engine or engines are running under maximum selected thrust. In addition, there are other conditions. The aircraft is in the highest possible critical configuration. The aircraft is loaded in the most permissible but least favorable extent. The trim is set for the approach. The aircraft weight is aerodynamically at its worst, and the maximum thrust is selected, i.e. the aircraft yaws maximally in the direction of the failed engine. Let's move on to the next V-speed, the VR. With the rotation, i.e. the lifting of the nose, the transition to the climb begins. The rotation should not be too fast. About 3 degrees per second will be ensured to avoid a tail strike. In order for the aircraft to be reliably maneuverable, the rotation speed must not be below the minimum controlled speed air, VMCA, which we have discussed. Immediately after VR, we reach the VLOF. At liftoff speed, sufficient lift is generated for the first time and the aircraft can overcome its own weight. Only now does it actually begin to fly. This speed is also based on calibrated airspeed. The legislator also attaches conditions to the speed. The takeoff speed must be at least 1.1 times the minimum unstick speed if all engines are available, and 1.05 times if the critical engine has failed. Now we are airborne, and the next speed we are looking at is referred to as the takeoff climb speed, V2. V2 ensures a climb even in the worst case when the critical engine has failed, and correspondingly less thrust is available because now more drag is generated on the side of the failed engine. In addition, a yaw moment is generated because the thrust now comes asymmetrically. And twin engine aircraft 100% from one side, and four engine aircraft more from the side on which two engines are still producing thrust. Yes, and the countermeasures must be taken against this yaw turning motion, which also generate aerodynamical drag. In case the critical engine has already failed, V2 must nevertheless be reached at 35 feet above the runway at the latest. And again, there are more requirements. V2 must be equal to or greater than 1.1 times the minimum controlled speed air. V2 must be equal to or greater than 1.13 times the Airbus-specific defined airspeed at which the aircraft can just maintain altitude immediately before stalling, abbreviated as VS1G, and V2 must be equal to or greater than 1.2 times the stalling speed, abbreviated VS. I will discuss stalls in a separate video. Let me now summarize. We have to talk about the definition of the so-called critical engine. In the takeoff phase, the VEF and the VMCG with the corresponding design-related requirements for the aircraft so that the pilot does not lose control. V1, the decision speed, takeoff aboard, yes or no. The V1 is very important and is calculated precisely every time so that either the takeoff can be safely aborted or the aircraft can be reliably brought into the air. Also important is the VMBE so that a takeoff aboard is possible at all. The V2 ensures that the aircraft is aerodynamically capable of a safe climb performance even in case of an engine failure. If the airspeed would drop below V2, the thrust still available would no longer be sufficient to continue climbing safely due to the increased drag. Obstacles in the departure sector, which would normally have been flown over without any problems, could then be the downfall. And we certainly don't want that. As we can see, there are a number of things to consider. The length of the runway, the loading of the aircraft, the position of the center of gravity, the meteorological conditions, i.e. outside temperature, air pressure, wind, dry runway or runway contamination, and the geomorphological specifications, field elevation, obstacles in the departure sector, and so on. All this plays a role in the calculation for V1, VR, and V2. Well, I hope you enjoyed my contribution. Sorry, yes, it's quite a dry topic, but very, very important. Very important topic. If you don't understand these correlations properly, you might get a not so nice surprise one day. And I certainly don't wish you on you. A feedback from you would be great. Thank you for joining me today. I'm happy if you stay and subscribe my channel. I still have some exciting topics for the future. Have a great day. See you soon.